focus is going to be on pH concept and calculation. So we started our acid unit with our last video, and we talked about how there's different pHs and how acidic or basic something is. We're going to be able to calculate that utilizing the concentration of hydrogen or hydroxide that is found in solution when acids or bases dissociate. Once we're able to figure out the concentration, we'll use a logarithmic scale to convert it into a number that hopefully makes a little bit more sense to everybody. So hopefully by the end of this video, you'll be able to understand the concepts of pH and how that applies to acidic or how basic something is. You should also be able to calculate four things: pH, pOH, hydronium ion concentration, and hydroxide concentration. We got some key terms here, the four things we just mentioned, as well as Kw, which we'll mention in just a moment. So when water, interestingly enough, is around other water, it can actually self-ionize into the constituent parts of acids and bases that we talked about. If you take a look on the right-hand side here, we have two water molecules. A hydrogen is donated from one water molecule to another, making one the hydrogen donator and the other the hydrogen acceptor. We talked about that as a Bronsted-Lowry definition of an acid or base. A Bronsted-Lowry acid donates a hydrogen while a base accepts it. And then we end up with hydronium, an acid, and OH minus, a base. Now the concentrations of these are actually very, very small in water. So we get 1 × 10 to the -7 moles per liter. So the concentration of it's actually quite small. But because this is an equilibrium expression, you notice the double arrow there, we can actually write an equilibrium expression for that. And we can say that Kw, or the equilibrium constant for water, is the hydronium concentration times the hydroxide concentration. So as a result, that gives us 1 × 10 to the -14th. Now, those numbers are really awkward to deal with. Anytime you have a very large exponent in a number, you know that can be very difficult to really comprehend and see. So we'll alter them, and we'll talk more about that a little bit later on. Now, when we change concentrations of strong acids and strong bases, can be calculated if we know the concentration of one. What that simply means is that if we know the concentration of an acid or base, we know the concentration of hydronium or hydroxide that will be found in the solution of that acid or base. Remember that strong acids and bases 100% completely dissociate. So, for example, if I have 2 molecules of HCl, I will have 2 molecules of H and 2 molecules of Cl when I put it into solution. That is because it 100% completely dissociates. So I can determine concentrations of solutions based off of this information. So for example here, it says what is the concentration of OH and hydronium in a 1.0 × 10 to the -2 molar NaOH solution? Well, we just talked about that. NaOH is a strong base. So whatever the concentration of the base is going to be the same as the concentration of OH. Okay? And if this were an acid, then the concentration of the acid would be the same as the concentration of the hydronium ion concentration, H3O+. So if I look right below my question, the OH is equal to the concentration of NaOH because all of it breaks down. So now that I know my concentration of OH is 1.0 × 10 to the -2, I can then plug that into my expression that we talked about previously. H3O plus times OH minus equals 1.0 × 10 to the -14th. So I plug my number in, and what I get is 1.0 × 10 to the -12th. So if you think about it, the solution is going to be more basic because the concentration of OH is 1 × 10 to the -2, and that is much greater than the hydronium ion concentration, which is 1 × 10 to the -12th. Okay? But again, those are really hard numbers to be able to comprehend. So what we do is we put them into a base 10 system. And as a result, we can use these logarithms to put things in a simpler term. So in order to calculate the pH of a substance, we take the negative log of H3O+. To take the pOH, we take the negative log of the OH concentration. So pH plus pOH is going to equal 14. When we take the log of something, essentially it kind of takes that exponent and moves it to the front. So our pH scale is based on 0 to 14. So if we look at our pHs, if the pH is greater than 7, it is a basic solution, meaning that the solution has more hydroxide or OH concentration than it does H3O+. If the pH is less than 7, it is an acidic solution, meaning that it has more hydronium ion concentration than hydroxide. Each number increase represents a tenfold difference. And that's really important to understand because this is a logarithmic scale. So for example, something that has a pH of 5 is 10 times more acidic than one of 6. So each time you go a number, it is a tenfold difference. So if I want to know the difference between 6 and 4, right, I would say that the substance that has the pH of 4 is 100 times more acidic than a pH of 6 because it is a log-based scale. But using the information we just talked about, you can calculate the pH, POH, OH concentration, and H3O plus concentration of everything we've been looking at. So my first question here asks me to determine the pH of a 1.0 times 10 to the negative fifth molar LiOH solution. So if I look here, this is LiOH. I know that because of the OH that this is a base. And I also know that because all of LiOH completely dissociates, that this is equal to my OH concentration. So there's a couple ways that you could go through and get the pH from this using the equations we've talked about before. We could take 1 times 10 to the negative 14th plug in H3O and our value for OH. That would give me my H3O concentration. I could also get the POH. Remember the POH is equal to the negative log of my OH concentration. Right? Either way, you will get the right answer here. And so I get the POH of this as being 5. And I remember that pH plus POH must equal 14. So my pH here is 9. And is this acidic or basic? Well, because the pH is greater than 7, this is a basic solution. Okay? So again, you just need to follow those formulas and remember that we can determine the concentrations of H3O plus and OH based on what chemical we are looking at. So this one here is a little bit trickier. We want to determine all of these things for something that has a pH of 4. So let's go ahead and get one of the easy ones out of the way. Well, we know that pH plus POH is 14, right? So I can get my POH pretty quickly. Just get rid of pH there and plug in 4, right? So I know my POH is 10. Good place to start, right? Now the question is, how do I work backwards? Because I know that the negative log, let's say H3O plus, is equal to my pH. So how can I work that around? Well, if I take this and move this over here, what we end up getting is a formula that we can do our concentration with. So we just have to take the inverse function of the negative log. So that's going to be H3O plus equals 10 raised to the negative pH. Okay? And it's the same way to find my OH concentration as well, except instead of using pH, we're going to use POH. So we plug those numbers in to our calculator. Right, we're just going to plug 4 in here, and we're going to plug 10 in there. And we should very easily be able to get our answers. You have 1 times 10 to the negative 10th. Oh, molarity, sorry. And H3O plus is 1 times 10 to the negative 4th. Okay. So again, the numbers won't always be as nice and even as that, but if you're utilizing those formulas, you should have no problem being able to solve any pH, POH one. Make sure you're also able to tell me if a solution is acidic or basic. Wrapping up a pretty short video here for today, so make sure you're able to understand these concepts of pH and how it applies, and then also make sure you're able to do all those calculations that we talked about. Hope you guys have a great day, and we will talk to you later. Bye-bye, guys.